All right, so we're going to say something about the existence and uniqueness theory for the solutions of differential equations. Okay. So let me sort of frame this basic problem. So we're going to look at initial value problems. So we're going to consider an initial value problem. So basically what's going to happen is that you have a differential equation which involves, say, the first derivative. It's like the function is equal to some other function which depends possibly on time, as well as that function y of t itself. And this holds for t greater than or equal to some initial time t0. And you also have the initial value of y. So y at t0 is equal to y0. Okay, so together this is an initial value problem where y of t is the unknown function which we're trying to solve for, right? Then you have t, which is just obviously time. Okay, and you have y0, which is the initial value. Okay, so let's look at a few examples of such initial value problems. Okay. So one possibility, for example, is to try to model population dynamics. Y of t is the population at time t. So so what usually happens, it's like in such a situation, is that the models for this involve the growth of the population, and usually one reasonable assumption to make is that the rate of growth of a population is proportional to the size of the population at that time, assuming that there are no, say, resource constraints which prevent the population from growing at that rate. So the rate of growth of a population with no resource constraints is proportional to the size of the population. Okay, and so we can encode it's like such a relationship by saying that the time rate of change of the population, which is y prime of t, right, is equal to some multiplicative factor k times the population at that time. So y prime of t is equal to k y of t, where k is some constant. So this could be various types of populations. It could be the size of a given city, for example. It could be, it's like the number of viruses it's like you have. It's like in a body. It's like in a host body, for example. Something along those lines, right? So of course it's like this is a simple equation, and the analytical solution to this, right, is just sort of exponential growth. So that's y of t is equal to some constant times e to the kt. Right, and actually you also know that if you have an initial value y0, right? So if y at some initial time 0 is equal to y0, then c is equal to y0. Okay, and then sort of the most general case is that, sort of more generally, right, if your initial data is that y at some initial time t0 is equal to y0, right, then the solution looks like y of t is equal to y0 e to the k t minus t0. Okay. All right, so that's just sort of a simple example of a differential equation. It's like, and if you add the initial condition, it's like then the combination of the differential equation and the initial condition gives you an initial value problem. Okay, so so let's look at one more example of this. Right. So this is sort of along the lines of these kind of population. It's like dynamics. Now we're going to look at a predator-prey system, which is called the Lotak-Volterra. It's like predator-prey equations. So Lotka-Volterra predator-prey equations. All right, and so now it's like you have two populations. Let's say f of t, which might be the number of foxes. Okay, so that's the predator. And then r of t is the number of rabbits. Prey in this case. Okay, and you have a coupled system of equations, of two equations, right? So r prime of t is equal to alpha minus beta ft times r of t. All right. So so the way to sort of interpret this is that the rate of change of the rabbit population has this growth term alpha times r of t, which we saw sort of in this case. It's like where we discussed the absence of resource constraints, but there's some rate of predation which has to do with the number of foxes, and that has a negative impact. It's like on the size of the rabbit population. So this is minus beta f t term multiplied into r of t, right? Okay, so that's one thing, and then there's the predator equation. F prime of t is equal to gamma r t minus delta. Okay, and then so basically the idea then is that you can think of this as population growth with a resource constraint, right? So we had sort of said that, well, you have this exponential growth. It's like when you don't have resource constraints. But of course, it's like if in any practical situation, there is a limit to how large a population can grow, because the growth depends on the availability of resources. So in the case of the foxes, that depends on the availability of rabbits. It's like for it to feed on. And so the basic idea then is that as there's a sort of, maximum population size, it's like for which the rabbit population can sustain, it's like the number of foxes there are, right? And so that term is representing the fact that there is this resource constraint which is dependent on the number of rabbits which are available, and that in addition to that, if there are lots of rabbits, that the growth can actually be faster, right? Anyway, so that's sort of again, it's like an idealized model. It's like of this predator-prey relationship, and you have a bunch of constants, alpha, beta, gamma, and delta, which are all positive, and they're constants. And of course, in both of these cases, they're sort of idealized. It's like mathematical models, but nevertheless, it's like they're kind of interesting things to study to get sort of a qualitative sense as to what are some of the important sort of it's like how, I guess, qualitatively, it's like these solutions change. For example, as you change these parameters, right? So it could be that as you go through certain critical values of these parameters, there's a dramatic qualitative difference in the behavior of the system. Okay. So the point, if you will, is that unlike the first equation which we discussed, right, which is just this, it's like situation. It's like where the time rate of change of the population is just proportional to its current value. There it is an analytical solution, but with the Volterra, it's like equation, right? This system of equations are not analytically solvable, right? So these equations cannot be solved analytically. So again, the basic point then, if you will, is that not all initial value problems, since I can be have an analytical solution, and this sort of is a motivation, if you will. It's like for development then of numerical methods for the solution of initial value problems, is that again, not all equations can be solved analytically, and so it is, but nevertheless, it's sometimes desirable to get some approximation of that solution, and that again naturally leads to the question of how to develop good numerical methods. It's like for that problem. Okay. All right. So that's one potential wrinkle. Not all equations have analytical solutions. There are other possible issues. So let me sort of just describe that. So the other issue is that sometimes solutions of initial value problems only exist locally. Okay, so sometimes solutions of initial value problems, right, exist only locally. So what do I mean by that? So let's consider this equation, right? Y prime is equal to y tangent t, and y at 0 is 1. Okay, you can check that one solution of this, right, is y of t is equal to 1 over cosine of t, right? And so this is, just write it this way, cosine of t. And this is obviously undefined, right, for t is equal to plus minus pi over 2. So the solution is only valid for the interval between minus 1/2 to 1/2. Sorry, minus pi over 2 to pi over 2. All right. So in addition to the observation that not every initial value problem, it's like has an analytical solution, the other observation is that even if the solution, okay, so that's a different thing. It's like the other issue is that if there is a solution, analytical or otherwise, it isn't always the case that the solution exists for all time. Okay, so so the first obvious question to ask is whether or not it's like a solution exists. Okay, so this is the question of existence. So we're going to try to address this. It's like by stating a local existence theorem. Okay, so we'll discuss a sort of local existence theorem. So when I say local, I usually mean in time. Here in this case. And this gives you sufficient conditions for an initial value problem, to have a solution locally so all it means to say that there's a sufficient condition is to say that if you satisfy this condition, then it's guaranteed that the initial value problem has a local and time solution. It doesn't guarantee that it exists for all time, but at least in some small neighborhood of the initial time t0, it's like that solution will continue to persist, okay? Or that solution exists and will continue to persist. So let me state the theorem, and this is what we call a local existence theorem. Okay, so the theorem is as follows, right? So again, this is for, let me just sort of remind you that this is for the setup where you have an initial value problem, right? Which is that y prime of t is equal to f of t y of t, right? Which is the differential equation. And then y at t0 is equal to y0. Okay, so that's sort of the setup which we're thinking about. Okay, and I'll state the theorem in the context of this setup. So, right. So the theorem as follows is that if f, which is this right-hand side, right, is continuous, in a rectangle, let's call it R, centered at the initial data, so t0, y0, where R is t comma y, such that t minus t0 is less than or equal to alpha, and y minus y0 is less than or equal to beta. Okay, so what I'm saying is something like this, right? This is the ty space as a point t0, y0, and there's a rectangle about that where the length in the y and t directions, right? So t is length alpha, and I mean, it's like the side of this rectangle, it's like in the t direction is actually 2 alpha, right? So I'm just measuring alpha from the center. It's like to one of the ends, and the height in this case is 2 beta. Okay, all right. So that's the center R. So we call this R. Okay, so if that's true, then the initial value problem, right, has a solution y of t, and there's a minimum existence time for this, right? For t minus t0 is less than or equal to the minimum of alpha comma beta over m, where m is a bound, it's like on the derivative, okay? Okay, so let's try to think about that, right? So, so you have this function f, which is continuous, all right, over this rectangle in space and time. That's sort of the way to think about it. And the claim is that, well, in that situation, then it is centered at the initial point t0, at initial time t0, and the initial value y0, right? You have this rectangle, it's like over which this, you know, the right-hand side, it's like of the differential equation is continuous. And then that solution exists starting at t0, y0, and it persists, it's like for a certain period of time, which is bounded from above, it's like by this alpha. So alpha makes sense, right? Because you start at initial time t0, and you sort of, you know, you evolve forward in time, and past the alpha value, the right-hand side is no longer guaranteed to be continuous, so it could behave very, very poorly. So you don't necessarily expect that the solution to persist. It's like past t0 plus alpha in the time direction. But in addition to that, the other idea is that as you move in time, the value can deviate, it's like from the initial value y0. Okay, and of course the worst case, the fastest case, or the fastest way it can deviate from the point y0, it's like, and potentially exit this rectangle, right, is the rectangle, it's like has radius, if you will, it's like has value beta, it's like from the center where you start off with, it's like to the boundary, right? So it's beta, but you have to divide it by the speed at which you can exit this, and the speed at which you can exit this domain is bounded obviously by the norm. I mean, it's like the maximum value, it's like of this right-hand side, right? So that's basically what this is. So this is the distance, it's like in the y direction divided by the velocity, and that gives you a unit of time, basically, right? So, your initial value problem then has a solution which is guaranteed to exist. It's like for this minimum of, you know, the amount of time it takes to exit the rectangle due to just moving in time, and then the possibility of exiting this rectangle, it's like in position space because of this velocity or the motion, it's like of the solution, it's like in y, okay, and you can within this time beta divided by m, where m is the maximum velocity in absolute value, you know that you can't go further, it's like from y0 than the boundary of this rectangle, it's like in this position sense. Okay, so that's sort of a very, very natural bound, all right, and in some sense this is the best you are guaranteed to have, but it also turns out that you actually do have existence of the solution, it's like in this time as well. Okay, so that's one issue. It's like this question of local existence in time. The other issue is, as I sort of stated, it's like in the title, it's like of this section, is the question of uniqueness of solutions. Okay, so the other problem is that you could have a differential equation, and if this right-hand side is not regular enough or not smooth enough in some sense, then you could have more than one possible solution to it. So let me give you an example of this. Okay, so the solution may not be unique. Okay, so let's look at an example. So we say we have y prime is equal to y to the 2/3 power, and that y at 0 is equal to 0. Okay, so you can check that there are two solutions. I'm going to give you two candidate solutions, and all you have to do to verify that they're indeed a solution of the differential equation is to substitute that into the differential equation and verify it satisfies that condition. And also you need to check that it satisfies the initial condition. All right. Okay, so you can check that y1 of t, which is identically 0, satisfies the equation because, okay, so if y of t is identically 0, when you differentiate it, that's 0, and that's, so the left-hand side is 0, the right-hand side is y to the 2/3. If y is 0, y to the 2/3 is also 0, so you get 0 equals to 0, which is sort of a tautologous statement, but you know, it's like it satisfies the differential equation. And then this bottom part, it's like y at time 0 is 0, which again is true because y is identically 0 for all time. So that's clearly a solution of this initial value problem. But there's another solution. You can also check that y2 of t equals to 1 over 27 t cubed is also a solution of this equation. Okay, so the point here then is that the solution is not unique. There is more than one. Okay, so so under what conditions then can we guarantee that you have a unique solution? Okay, so let me state that theorem. Okay, so this is local existence and uniqueness. Okay, so if f and df, partial f respect to the y value, right, are continuous in the rectangle R, so we have the same setup here, right, then the initial value problem has a unique solution. Y of t, right, for t minus t0 less than equal to this minimum of alpha and beta beta divided by m as before, where m is the same as before. So m is equal to the maximum over r of the absolute value of f of ty. Right? So that's the same as condition we had before. All right. So let's check that, right? So you can check that basically the part which this differential equation doesn't satisfy is df dy. It's like being continuous. So f is y to the 2/3 power. When you differentiate that, that's not continuous at y equals to 0, which is the initial value here, right? So so here it's like t0 is equal, let me just put it this way, here t0, y0 is equal to 0, 0. And again, the point is that the derivative of that right-hand side, y to the 2/3, is not continuous at, it's like at the initial point, basically. So as a consequence of that, this differential equation does not satisfy, it's like the sufficient conditions for, local existence and uniqueness. And so it turns out the solution exists, but again, the solution is not unique, okay? All right, so finally, it's like, so far we've been talking about a local theorem. Let me say something about global sort of existence and uniqueness, all right? Global existence and uniqueness. Okay, so you assume that sort of t0 lies in the interval between a and b, right? So if f is continuous in the strip okay, in this interval, right, between a and b, and okay, so it's not, it's not just that between a and b. You also need that it's also continuous in this thing where y is allowed to be any value, right? So there's no constraint on y, but there's a constraint on time. Okay, so that's basically saying that if you have if you have a and b, right, that on this strip, right, so this is time, and then this is y. So on this strip, the function f is continuous, right? And there's also a further condition, and uniformly Lipschitz continuous. Okay, in y. So what do I mean by that? Okay, so this is a stronger condition than continuity. Okay. So what it says is the following, that there exists some Lipschitz constant L greater than 0 such that for all y1 and y2 and for all t in the interval between a and b, right, the difference between f at t comma y2 and f at t comma y1. So what is happening here is that you're evaluating f at two different positions, but the time remains the same. Okay, so this is why we're referring to Lipschitz continuity in y, right, in this variable y. We're not asking for continuity. Well, I mean, we're not sort of saying something here about t, and this is sort of analogous, or is a stronger condition than the property that df dy, right, partial f in the y direction is continuous. Okay. So, so this Lipschitz continuity actually implies it's like that df dy is continuous, but it's stronger. Okay. All right. And this is less than equal to L times the difference between y2 and y1. Okay. So let's try to parse this, right? So modulo this uniformity part, this Lipschitz continuous in y part is this statement. All right. So where the uniformity part comes from is that if you just said that f is Lipschitz continuous in y, it is possible that this Lipschitz constant L depends on t, okay? And the uniformity part comes from the condition that this L can be, L of t in principle can be replaced, it's like by some L for all t in the interval from a to b. So that's where the uniformity comes from, is that this L doesn't depend on t, all right? It's okay, so in any case, it's like if you have this uniform Lipschitz continuity of the sort of the vector field in the y direction, then the initial value problem has a unique solution in the time interval from a to b, right? Then the IVP has a unique solution in the interval from a to b, the time interval from a to b. And of course, you can imagine it's like extending the time interval, right? All right, so anyway, so this is sort of the basic theory, it's like of solutions of differential equations. It tells you under what circumstances, you know, you have a solution, possibly for a short time, it's like, or possibly over an entire time interval. And then again, under what conditions, it's like the solution is unique, okay? And so that's important, of course, because if you don't have existence and uniqueness of solutions, then it doesn't make sense to go and try to find a numerical solution of the differential equation. All right, and again, the motivation for studying numerical solution of differential equations is because not every single initial value problem has a analytical solution to it, and so that naturally leads us to consider numerical approximations as well. Okay. All right. So let me just stop here for a little bit, and then the next thing I'll talk about is this notion of well-posedness. So I'll stop here for now.